Chapter 6, Structures. At the very beginning of this semester, we talked about some system building blocks. We talked about multiplier that multiply the input with a scalar alpha, and we have talked about adders that adds up two input together and delay the input by 1 unit of time. In this chapter, we are going to be talking about structure. That is, given a rational system HC, how do we implement HC using the three building blocks: multipliers, adders, and delays. For example, suppose we have a second order system HZ here. It has 1 plus a1z inverse a2z minus 2 raised to the power minus 2 and a numerator with coefficient b0, b1, and b2. How do we implement it? We can get a clue from the difference equation. For such a system, we know how to write down the difference equation. Yn can be written in terms of xn, xn minus 1, xn minus 2, yn minus 1, yn minus 2. Yn can be written as a linear combination of these signals with linear combination coefficient b0, b1, b2, minus a1, and minus a2. Now suppose we have xn here. This is the input, and we will need xn minus 1. So we put a delay and another delay because we also have xn minus 2. So the signal here, the output of the delay here is xn minus 1, and the output of the next delay is xn minus 2. And these will be multiplied with coefficient. These signals will be multiplied with coefficient. In particular, xn is multiplied with b0, xn minus 1 with b1, and xn minus 2 with b2. And then these signals will be added up. They will be all added up. Alright, so we have the first three terms. Alright, now we still need yn minus 1 and yn minus 2. So suppose this is yn here, then we will need yn minus 1, yn minus 2, and these will be multiplied with a coefficient. For yn minus 1, it's minus a1, so we multiply it with minus a1, and yn minus 2 will be multiplied with minus a2. The output of the delay is yn minus 1 and yn minus 2. Alright, and then we are going to add them up too. We will add them up with the parts from xn. Add them all up. Well, after we add them all up, what we get is yn right here. So this is yn. Yn has b0xn, b0xn coming in here, b1 xn minus 1 coming here, b2 xn minus 2, add them all up, and then m minus a1, yn minus 1, minus a2, yn minus 2. All these terms will be added up to get yn. An implementation like this, based on the difference equation, is what we call a direct form 1 structure. This structure will implement the difference equation directly. Now a question. Suppose I call this a signal right in the middle here, wn, and I call the part from xn to wn. This part I call the system H1 of Z. And from wn to y, this part of the system, we call it H2C. Now the question, in this implementation, first we have xn, and then we pass it through H1C to get wn, and then we pass through H2C to get yn. Now suppose I interchange the order of the two. First I pass it through H2 first, and then H1. Well, then of course the signal here won't be wn anymore. And do I get the same y? Do I get the same y? Both H1 and H2 are LTI systems. So when we interchange the two, do we get the same system? Yes, we do. We still get the same system. So we can interchange the two. So we first move F2 here. And let's say the signal here is Tn. And right here we have Tn minus 1. This is Tn minus 2. And the coefficient here is minus A1 minus A2. So this is H2, right? And now let's move H1 in here. First we have a delay. And then another delay. And we have B1. We have B2. This is B1. And we move H1 here. So now from this part to this part, we have H2. The output of H2 is Tn. And from this part to this part, it's H1. T1 is Tn is the input, and Yn is the output. Now, let me ask another question. The signal here, this is T, right? We call the output T here. And the output of the delay here is Tn minus 1 right here. And the output here is Tn minus 2 here. How about the output here, the output of this delay? What is this signal? Let's find out. This is Tn. Tn is right here. So this is Tn. Tn goes, at this point, Tn goes two-way. One to here, and the other one to the other way. And this is Tn. So the input here is Tn. So the output of this delay is also Tn minus 1. This is also Tn minus 1. How about the output of another delay? Right here. It's Tn minus 2, isn't it? So the numbers that are stored in this delay element and this delay element are actually the same numbers. And the number that is stored in this delay element and this delay element are again the same numbers. So can we combine these two delay and these two delay together into one? We can, because they are the same numbers. So what would the picture look like if we combine them? Suppose we have xn and tn here, and then we would just have one set of delay, and the delay here would be multiplied with the minus a1 minus a2. The output are added together, and then here again we have another adder. And on the other hand, we would have B0 and B1, B2, and the output are added together. And this is Yn. This is B2. So now we have a different structures. This new structure is what we call direct form 2 structure. This is direct form 1, that's implemented based directly on the difference equation. And to get direct form 2, we interchange H1 and H2 and combine the two sets of delay. We get the direct form 2 structures. Direct form 2, here it has only one set of delay, is what we call a canonical form. What's the meaning of a canonical form? That means that the implementation with the smallest number of delay. For example, here we have a second order system, so the smallest number of delay is 2, and we use only 2 delay here. This is a canonical form. When we look at the structure, we often want to know the complexity. Let me write down the scratch paper here. Complexity of the system. That means the cost of implementing the system. The cost is usually related to the building blocks that we have used. How many multipliers we have used, how many number of delay we have used, and what's the number of adders that we have used. Delay, multiplier, abbreviation MOL, and adders, abbreviation add. How many delay do we need here? We need 2. And multiplier, how many multipliers? We have 1, 2, 3, 4, 5 multiplier. How about the number of adders? We have 1, 2, 3, 4 adders. So that's the number of building blocks. That's the numbers of a different number of different building blocks that we need here. So based on the system function, we can write down the difference equation, and from the difference equation we have the direct form 1 and direct form 2 implementation. This is an example of a second order. How about general nth order? For a general nth order, we have B0, B1 all the way to Bn, and the coefficient here is 1, B1 all the way to An. We have normalized the coefficient so that the leading coefficient here is equal to 1. If we have A0 here and B0 here, we can always normalize it so that the coefficient here is 1. And for the difference equation, we will run all the way to Bn xn minus big N. And for y, we have yn minus 1, yn minus 2, all the way to yn minus n. For the implementation in direct form 1, now we would have xn minus 1, xn minus 2, all the way to xn minus n. If we look at this is like a square, this is another square. For the second order case, we have 2 squared, and for the nth order case, we would have n squared. So at the bottom, we have n squares. This is b, n minus 1. This is bn, and continue on like this. And on the other side, we would also have n squares minus an minus an minus 1 like so. Similarly, with the direct form 2, for nth order case, we now have delay that goes on with -1. This is Bn, and this is Bn -1. Continue on like this. This is -an, and that's -an -1. Alright, so that's for the nth order case, direct form 2. Again, this is a canonical implementation that is implemented with the smallest number of delays. We can write down the number of delays that's needed in this case. Now is n. How about the number of multipliers? We have n multipliers plus 1. So we have 2n plus 1. How about adders? We have n here and n here. So together we have 2n. So that's the number delay, multipliers, and adders that are needed in the direct form 2 structure. When we draw the system implementation, we often want to draw it in a simple and understandable way. Take this second order system that we have drawn earlier as an example. We would like to simplify it so that we don't need to draw a box for the inverse and the inverse. And we also want to draw the multiplier in a little bit more simpler way. Let's take this second order system as an example and convert it to a signal flow graph. In a signal flow graph, we have node. This is the input. Input is what we call the source node, and the output is what we call the sink node. And between the input and output, we have boxes like this, and then here we have -a1, -a2. Now, for the multiplier, we simply use arrows. This is B0, B1, B2. And for the delay, we also use arrows. It's an appropriate notation in the sense that when a signal is passed through a delay in Z transform, it is with Z inverse. And now we also have adding up, right? This is an adding up node. This here's input, and at this node we have adder here, and this is what we called an adding node. And for this one, when the input comes in, and this is also an adding node because it has 2 input and 1 output. Whereas for this one it has 1 input and 2 outputs. It has 1 input and 2 output, so it's no longer an adding node, it's a branching node. And similarly, this will be a 1 input, 3 output, so this is also a branching node. 1 input, 2 output, a branching node. How about this one? This one, 1 input, 2 input, so this is a 1 output. So this is a branching 1 input, 2 inputs, and 1 output. So this is a adding node, also an adding node. And for this one, it has 2 inputs and 1 output, so also an adding node. So let me mark the adding node with green, green, green. These two are adding node, and these two are also adding node, and the rest are branching node. And if we are given a graph like this, we say this is a signal flow graph, although it does not have headers and it does not tell us which one is adding node, which one is branching node, but you can still see that it's a branching node or an adding node just by looking at the input and the output. Whenever we have more than one input, then the node will need to add them together. So we have adding node. And if we have one input and more than one output, then that will make it a branching node. One more term, the line that connects two nodes together here is what we call a branch. So here we have a branch. This is called a branch. So a signal flow graph is actually a graph that consists of nodes and branches. We have a bunch of nodes and the branches that connect the nodes together. That will make a signal flow graph. Just now we have talked about direct form 1 and direct form 2 structures. Given a system function, we have more than one way of implementing it. But actually, there's more. A result here, transpose form, it tells us that given a flow graph or given an implementation, we can use what we call transposition of a structure to get a new structure. So given an implementation, we can use the result here to get a new implementation. And the method here, transposition, is this way. Suppose we are given a signal flow graph of a system HC, where the signal flow graph can be derived from 1, can be derived from 2, or any other implementation that we can come up with. If the directions of all branches are reversed, the system function of the transpose form remains the same. Let's use the second order type 2 direct form implementation as an example for transposition. We take this signal flow graph and now let's reverse all the direction. But first let me plot all the nodes. We still get minus A1, minus A2, B1, B2, and B0. That's not changed. And now let's reverse the direction of all the nodes. Okay? So for example, xn here would be this coming. This is going right. Now if we reverse the direction, you'll be going left. Okay? And this going right, it would all become going left, left. Delay here is going down. Now it would become going up. Still we have delay. And the direction here is going up. This one is also going up. Now it's going down. Similarly, this is going down. And for the here, this is going left. These two are going left. These two are going right. So we would have going reverse direction. And here is also in this direction. Alright, so where is our input now? This, of course, is our input coming in. And this is our output going out. So when we're reversing all the branches, the input node becomes the output, and the output becomes the input. The source node becomes the sink node, and the sink node becomes the source node. In this transpose structure, the input is coming in on the right and the output is going out on the left. But usually we would like to have the input coming in from the left. So let's redraw it, and the more style that we are familiar with. So the input is coming in on the left and the output is going out on the right. Now it's like we are taking a mirror image of the picture above. So we see that when the input is coming in, first this is going this way and then this way. So now we would have this coming this way and then this way in the direction that the input is coming in. When it first comes in, there is a one input, two output node. So this will make it a branching node or adding node. It will be a branching node. So here we have a branching node. If we continue on down, here it have a one input, one output, two outputs. So it will make it a branching node as well. So here it's going this way. And then another branching node. This is a B1 and this is a B2. And if we have gone this way, here is a B0. And here we have a one branch in, two branch in. That will make it a adding node. So right here, we have a adding node. This is going up, the inverse. And then another the inverse going up. And right here, if we look at this point, we would have one input, two inputs, three inputs, and one output. So that will make it a adding node as well. Right here, this is an adding node. And if we go down, right here, we have a one input, two inputs, and one output. So that will make it a adding node. Right here we have, this is minus A2. And this one above is minus A1. And here it's going down, going down. And there we have complete the transpose structure of direct form 2. And let me write it down. This is a transpose direct form 2. And if we compare it with the direct form 2 that we drew earlier, this is a different implementation. When we reverse the direction of all the branches, for example, this branch here, it has one input, two inputs, and one output. This is the adding node actually. But after we reverse the direction of all the branches, it now has two outputs and one input. So originally this was an adding node, but now it has become a branching node. So all the adding nodes are converted to branching node when we reverse the direction of all the branches, whereas a branching node will become an adding node.